Tonight, we're going to explore a particle that has never been detected. A particle that might not even exist, and yet its very possibility threatens to unravel the most fundamental rule the universe has: cause and effect. Because buried inside the mathematics of Einstein's special relativity is something deeply unsettling. If anything could travel faster than the speed of light, then in certain frames of reference, it wouldn't just arrive quickly. It would arrive before it was sent. The effect would happen before the cause. Time itself would run backward. Not as science fiction, not as metaphor, as mathematics. Cold, clean, unavoidable mathematics. And the implications of that are so profound, they challenge everything we think we understand about how reality works. Before we get into this, if you find these kinds of deep explorations interesting, a quick like or subscribe really helps the channel out. It's a small thing for you, but it makes a really big difference for me. Now, get yourself nice and comfortable. Let's begin. Let's start with something that seems like it should be obvious, but is actually one of the strangest discoveries in the history of science. Light always travels at the same speed. Always. No matter what. No matter who is watching. No matter how fast you are moving. No matter where you are in the universe. The speed of light in a vacuum is exactly 299,792.458 kilometers per second. We usually round this to about 300,000 kilometers per second for simplicity, but the precision matters because this number has been measured with extraordinary care using lasers, atomic clocks, and interferometers so sensitive they can detect changes smaller than the diameter of a proton. This speed is not an approximation. It is one of the most precisely measured quantities in all of physics, and it never changes. Not for anyone. Now you might be thinking, okay, light is fast. What's the big deal? Everything has a speed. Cars have a speed. Sound has a speed. Bullets have a speed. Light just happens to be faster than all of them. But here's where it gets strange. The speed of light does not behave the way any other speed behaves. Every other speed in your daily experience is relative. It depends on who is measuring it and how they are moving. If you are standing on the side of a highway and a car passes you at 100 kilometers per hour, you measure its speed as 100 kilometers per hour. But if you are in another car driving alongside it at 80 kilometers per hour in the same direction, you measure the first car as moving at only 20 kilometers per hour relative to you. Speeds add and subtract. This is common sense. It's something you understand intuitively because you have experienced it your entire life. Now, imagine you are on a spacecraft traveling at half the speed of light. That is 150,000 kilometers per second. Incredibly fast. You turn on a flashlight and point it forward. The light leaves the flashlight and travels ahead of you. From your perspective aboard the spacecraft, the light moves away from you at 300,000 kilometers per second. That makes sense. You turned on the flashlight and the light goes forward at light speed. Now here is the part that should bother you. Someone standing still, watching your spacecraft fly past, also measures the speed of that flashlight beam. And what do they get? Not 450,000 kilometers per second, which is what you would expect if speeds added the way they do for cars on a highway. They get 300,000 kilometers per second, exactly the same number you measured. The light is not moving faster from their perspective, even though you, the source of that light, are already moving at half the speed of light. Both of you, the moving observer and the stationary observer, measure exactly the same speed for the same beam of light. This is not a thought experiment that has yet to be verified. This has been tested. It has been confirmed over and over again for more than a century. The most famous early test was the Michelson-Morley experiment in 1887. Albert Michelson and Edward Morley set up a device called an interferometer that split a beam of light into two paths, one aligned with Earth's direction of motion through space and one perpendicular to it. The idea was simple. If the speed of light depended on your motion, then the two beams would travel at slightly different speeds because one would be moving with the Earth and one across it. When the beams were recombined, this difference would show up as a shift in the interference pattern. They ran the experiment. There was no shift. None. The speed of light was the same in both directions regardless of Earth's motion. They repeated the experiment at different times of day and different times of year as Earth changed its direction of motion around the Sun. The result was always the same. The speed of light did not depend on the motion of the observer or the source. This result was so unexpected that physicists spent nearly 2 decades trying to explain it before Einstein offered the answer in 1905. His solution was radical. He did not try to explain why the Michelson-Morley experiment failed. Instead, he accepted the result at face value and asked a different question. What would the universe have to look like if the speed of light really is the same for everyone? The answer turned out to be special relativity, and it changed everything. Einstein built special relativity on 2 postulates, just 2 simple statements. First, the laws of physics are the same in all inertial reference frames. An inertial reference frame is one that is not accelerating. It is either at rest or moving at a constant velocity. This first postulate says that no inertial frame is special. There is no experiment you can do inside the sealed laboratory moving at constant velocity that will tell you whether you are moving or stationary. Physics works the same way everywhere, for everyone, as long as they are not accelerating. This was not a new idea. Galileo had expressed a version of it centuries earlier. The second postulate was the revolutionary one. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the source. This was the bombshell. This was the statement that broke our intuition about how speeds combine. And from these 2 postulates, everything else follows. If the speed of light is the same for everyone, then something else has to give. Speeds cannot add the way we expect them to. And if speeds do not add normally, then the measurements that go into calculating speed, distance, and time must themselves be different for different observers. This is exactly what Einstein showed. He demonstrated that time itself passes at different rates for observers in different states of motion. This is called time dilation. He showed the distances along the direction of motion actually contract. This is called length contraction. And he showed that the energy required to accelerate an object increases without bound as the object approaches the speed of light, meaning that no object with mass can ever reach it. These are not abstract theoretical predictions. They have been measured directly and confirmed with extraordinary precision. Let me give you some of the evidence because it matters. If special relativity were just a beautiful mathematical theory with no experimental support, It would be interesting, but not compelling. The reason physicists accept it so completely is that every single test, every single measurement, every single observation has confirmed it. Particle accelerators are one of the most powerful testing grounds. When protons or electrons are accelerated to speeds approaching the speed of light, their behavior changes in exactly the way special relativity predicts. Their effective inertia increases. They become harder and harder to accelerate. At the Large Hadron Collider, protons are routinely accelerated to 99.9999% of the speed of light. At this speed, the proton's effective inertia is over 700 times greater than its rest inertia. The accelerator has to pump in enormous amounts of energy to nudge the proton even slightly faster. And no matter how much energy you add, the proton never reaches the speed of light. It gets closer and closer, 99.99999%, but it never arrives. The speed of light is not a wall you can hit. It is a limit you can approach forever without ever touching. Time dilation has been measured directly using atomic clocks. In 1971, physicists Joseph Haffel and Richard Keating placed extremely precise cesium atomic clocks on commercial airliners and flew them around the world, once eastward and once westward. When the clocks were compared to reference clocks that had stayed on the ground, the flying clocks had ticked at different rates. The differences were tiny, measured in nanoseconds, but they were exactly what special relativity and general relativity together predicted. Time literally passed at a different rate for the moving clocks. This was not a malfunction. This was not a measurement error. This was time itself behaving differently depending on motion. GPS satellites provide another beautiful confirmation. The Global Positioning System relies on a constellation of satellites orbiting Earth, each carrying an atomic clock. These clocks are moving at about 14,000 kilometers per hour relative to the ground. Special relativity predicts that the satellite clocks should tick slightly slower than clocks on the ground, losing about 7 microseconds per day. General relativity, which deals with gravity, predicts that the clocks should tick slightly faster because they are in a weaker gravitational field, gaining about 45 microseconds per day. The net effect is that the satellite clocks gain about 38 microseconds per day compared to ground clocks. This might sound tiny, but if GPS did not correct for this effect, position errors would accumulate at a rate of roughly 10 kilometers per day. Within a few hours, your GPS would be wildly inaccurate. The fact that GPS works, that it can pinpoint your location to within a few meters, is direct proof that time dilation is real. Cosmic rays provide yet another confirmation. When high-energy protons from deep space slam into molecules in Earth's upper atmosphere, at altitudes of about 15 to 25 kilometers, they create showers of secondary particles. Among these particles are muons. A muon is an unstable particle with a mean lifetime of about 2.2 microseconds. At this rate, even if a muon were traveling at the speed of light, it should only be able to travel about 660 meters before decaying. But the muons are created at altitudes of 15 to 25 kilometers. They should decay long before reaching the ground. And yet, we detect muons at ground level all the time. Moon detectors on Earth's surface pick them up constantly. How is this possible? Because the muons are moving at nearly the speed of light, and at that speed, time dilation stretches their lifetime. From our perspective on the ground, the moon's internal clock runs slow. Its 2.2 microsecond lifetime gets stretched by a factor of 10 or more, giving it enough time to reach the surface before decaying. From the moon's perspective, something different but equally valid is happening. The moon's own clock runs normally, but the distance between the upper atmosphere and the ground is length contracted. The distance is shorter from the moon's frame, so it does not need as long to traverse it. Both explanations give the same result. The muon reaches the ground. Both are correct in their respective frames. This is not a paradox. It is the consistent logic of special relativity. Now, all of this leads to something deeper. The speed of light is not just a fast speed. It is a structural constant of space-time itself. To understand what this means, we need to think about space-time in a way that goes beyond our everyday experience. In our daily lives, we think of space and time as separate things. Space is where things are. Time is when things happen. They seem completely different. Space has 3 dimensions. You can move left and right, forward and backward, up and down. Time has 1 dimension, and you can only move forward through it. But in 1908, 3 years after Einstein published special relativity, the mathematician Hermann Minkowski showed that space and time are not separate. They are woven together into a single 4-dimensional structure called space-time. Minkowski famously declared that space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. In Minkowski's space-time, every event, everything that happens, is a point with 4 coordinates. 3 spatial coordinates and 1 time coordinate. Your birth is 1 point. You listening to these words right now is another point. Every event that has ever happened or will ever happen occupies a specific location in this 4-dimensional structure. And the geometry of this structure is not like the geometry of ordinary space. In ordinary space, the distance between 2 points is always positive. But in space-time, the interval between 2 events can be positive, negative, or 0, depending on the relationship between the spatial separation and the time separation. The speed of light defines the boundary between different kinds of intervals. If you pick any event and draw all the paths that light could take from that event, those paths form a cone in space-time. This is called the light cone. The light cone has 2 parts. The future light cone contains all the events that light from the original event could reach. The past light cone contains all the events from which light could have reached the original event. Events inside the future light cone can be caused by the original event. Events inside the past light cone could have caused it. Events outside the light cone in any direction are called space-like separated from the original event. They are too far away in space and too close together in time for even light to connect them. No signal traveling at or below the speed of light can reach from one to the other. This is where the speed of light stops being merely a fast speed and starts being a law of causality. The light cone defines which events can influence which other events. If event A is inside the past light cone of event B, then A could have caused B. A signal could have traveled from A to B at or below the speed of light, carrying information, carrying influence, carrying a causal connection. But if event A is outside the light cone of event B, if they are space-like separated, then A cannot have caused B and B cannot have caused A. No information, no signal, no influence of any kind can travel between them. They are causally disconnected. This is an absolute statement. It does not depend on who is observing. It does not depend on your frame of reference. Every observer in every inertial frame agrees on whether two events are inside or outside each other's light cones. The classification is invariant. It is a feature of the geometry of space-time itself, not a feature of any particular observer's perspective. This is what makes the speed of light so fundamental. It is not merely the fastest speed that happens to exist. It is the speed that separates events that can be causally connected from events that cannot. It is the speed that defines the structure of cause and effect in the universe. And cause and effect is everything. Without a consistent ordering of cause and effect, physics does not work. Prediction becomes impossible. If an effect could happen before its cause, then you could never determine what would happen next, because what happens next might already have been changed by something that has not happened yet. The entire framework of physical law depends on causes preceding effects. The light cone is what guarantees this. As long as every signal, every influence, every causal connection travels at or below the speed of light, the causal order of events is preserved. Everyone agrees on what caused what. The universe makes sense. Now, there is a subtlety here that will become critical as we go deeper. The light cone protects causal order absolutely for events that are time-like separated, meaning events close enough together in space and far enough apart in time that light could travel between them. For these events, every observer agrees on which happened first. The time ordering is universal, but for events that are space-like separated, the situation is different. Different observers in different frames of reference can actually disagree about which event happened first. This sounds alarming, but it is not, at least not yet, because space-like separated events cannot influence each other. No signal at or below light speed can connect them. The disagreement is harmless because no causal connection exists between the events. But this harmlessness rests on a single assumption, that no signal can travel faster than light. If that assumption holds, the disagreement about space-like separated events is just a curiosity, an interesting feature of space-time geometry with no physical consequences. But if it fails, the consequences could be severe. To understand exactly how severe, we first need to understand a deeper feature of space-time, one that makes the disagreement about ordering far more dramatic than a simple difference of opinion. We need to understand why now is not the same for everyone. We need to understand the relativity of simultaneity. The speed of light sets the rules. It defines the playing field. It determines which events can cause which other events. It is the absolute constant around which all of space-time is organized. Every experiment ever conducted, every observation ever made, every measurement ever taken is consistent with this. The speed of light is the same for everyone, in every frame, everywhere in the universe. And that single fact has consequences far stranger and far deeper than most people realize. We have only just begun to see what those consequences are. To understand what a faster-than-light particle would do to the universe, you first have to understand something about time that most people never think about. You have to understand that now is not universal. The moment you call right now, this very instant as you are hearing these words, is not the same instant for someone moving at a different velocity. Two events that happen at the same time for you might happen at different times for someone else. And this is not an illusion. It is not a trick of perception or a delay caused by the time it takes light to travel. It is a real, physical, measurable feature of how space-time works. Different observers in different states of motion genuinely disagree about whether two events happen at the same time. And they are all correct. This is called the relativity of simultaneity, and is one of the most counterintuitive consequences of special relativity. It sounds wrong. It feels wrong. Everything in your daily experience tells you that now is now for everyone. When you clap your hands, that clap happens at a specific moment in time, and surely everyone in the universe agrees on when that moment is, regardless of how they are moving. But they do not. And proving this does not require exotic equipment or billion-dollar experiments. It only requires a thought, experiment that Einstein himself devised. One so elegant and so simple that once you understand it, you cannot unsee it. Imagine a train moving at a very high speed along a straight track. In the exact middle of the train stands a passenger. At the exact moment the passenger is directly opposite a person standing on the platform, two bolts of lightning strike the train simultaneously, one at the front and one at the back. The platform observer sees both strikes happen at the same time. They are standing at the midpoint between where the two strikes hit, and the light from both strikes reaches them at the same instant. The platform observer concludes, correctly, that the two lightning strikes were simultaneous. Now consider the passenger on the train. The passenger is also at the midpoint of the train, exactly halfway between the two strike points, but the train is moving forward. After the lightning strikes, the light from both strikes begins traveling toward the passenger at the speed of light. But during the time the light is traveling, the train is moving. The passenger is being carried toward the front of the train and away from the back. This means that light from the front strike has a shorter distance to travel to reach the passenger, and the light from the rear strike has a longer distance to travel. Since both light signals travel at exactly the same speed, the speed of light, the signal from the front arrives at the passenger first. The passenger, standing at the midpoint of the train and knowing that light travels at the same speed in all directions, concludes that the front lightning strike happened before the rear lightning strike. The front strike must have occurred earlier because its light reached the midpoint first, even though both signals traveled at the same speed. The passenger is not making an error. The passenger is applying the same laws of physics that the platform observer applied. The passenger is using the constancy of the speed of light, the very same postulate that defines special relativity, and arriving at a different conclusion about the timing of the two events. The platform observer says the strikes were simultaneous. The passenger says the front strike happened first. Who is right? Both of them. Both observers are in valid inertial reference frames. Both are applying the laws of physics correctly. Both are making accurate measurements. The disagreement is not a mistake. It is a fundamental feature of space-time. Simultaneity is relative. Two events that are simultaneous in one frame are not simultaneous in another frame that is moving relative to the first. Let me be very clear about what this means, because it is easy to dismiss this as some kind of optical illusion or measurement artifact. It is not. This is not about light taking different amounts of time to reach different observers. If you carefully account for the travel time of light, if you set up synchronized clocks at every point along the train, and along the platform, you still get the same result. The platform clocks say the 2 strikes happened at the same time. The train clocks say the front strike happened first. The clocks are not broken. They are not desynchronized due to some technical failure. They are correctly measuring time in their respective frames, and the measurements genuinely disagree. To understand how deep this goes, let me give you another scenario. Imagine you are floating in space, perfectly still relative to the stars. Far away to your left, 100 light years away, a star explodes in a supernova. Far away to your right, also 100 light years away, a different star explodes. In your frame, these 2 explosions happen simultaneously. They occur at the same moment on your clock, separated by 200 light years of space. You witness this cosmic symmetry, 2 stars dying at the same instant, perfectly balanced on either side of you. Now imagine an astronaut flying past you at 80% of the speed of light, heading to the right. This astronaut observes the same 2 explosions, but in a frame, the timing is completely different. The explosion on the right, the one she is traveling toward, happened decades before the explosion on the left. Not seconds, not minutes, decades. This is not because the light reached her at different times. She has already accounted for that. She has set up synchronized clocks across her reference frame. She has corrected for every light travel delay. And after all those corrections, she concludes that the right supernova genuinely occurred decades before the left one. That is the reality in her frame. Now imagine a different astronaut, traveling at the same speed but in the opposite direction, heading to the left. For this astronaut, the left supernova happened decades before the right one. The exact reverse ordering. 3 observers, 3 different temporal orderings of the same 2 events. One says they were simultaneous, one says the right explosion came first by decades. One says the left explosion came first by decades. All 3 are correct in their own frames. There is no fact of the matter about which ordering is really true. The ordering depends on the observer's state of motion, and no state of motion is privileged over any other. That is what the first postulate of special relativity guarantees. No inertial frame is special. No observer has a better claim to truth than any other. This becomes even more striking when you think about what now means across large distances. If someone asked you what is happening right now on a planet orbiting a star 50 light years away, you cannot give a meaningful answer. Not because you lack the information, although you do, but because right now at that distance is not a well-defined concept. It depends on your motion. If you are sitting still, your now at that distant planet corresponds to one moment. If you stand up and start walking to the east at a normal walking pace, your now at that distant planet shifts. Not by much, by an incredibly tiny amount at walking speeds, but it shifts. Your plane of simultaneity, the set of events across the universe that you would call happening right now, tilts when you change velocity. At walking speeds, the tilt is immeasurably small over short distances. But across 50 light years, even that tiny tilt can shift your now by several seconds. That might not sound like much, but extend the principle to the Andromeda Galaxy, 2.5 million light years away, And the same walking speed difference shifts your now by days. Someone walking east and someone walking west, standing right next to each other on Earth, disagree about what is happening right now in Andromeda. For one of them, a particular event in that distant galaxy has already happened. For the other, it has not happened yet. This is the relativity of simultaneity applied to cosmic distances, and it reveals something startling about the nature of time. There is no universal present moment. There is no cosmic now that extends across the universe like a sheet of glass, with everything on one side being the past and everything on the other side being the future. Instead, the division between past and future depends on where you are and how you are moving. Your present, your now, is personal. It is defined by your state of motion. And it can differ from someone else's present, even if that someone is standing right next to you. This happens because of how time and space transform when you change reference frames. In classical physics, the physics of Newton, switching from one frame to another was simple. You adjusted the spatial coordinates to account for the relative motion, but time stayed the same. Everyone agreed on time. Clocks ticked at the same rate for everyone, and simultaneity was absolute. But special relativity showed that this is not how the universe works. When you switch between inertial frames moving relative to each other, both the spatial coordinates and the time coordinates change. The transformation that describes this is called the Lorentz transformation, named after the Dutch physicist Hendrik Lorentz, who developed the mathematical framework that Einstein later gave physical meaning to. The Lorentz transformation tells you how to convert the coordinates of an event measured in one inertial frame to the coordinates of the same event measured in another inertial frame, moving at a constant velocity relative to the first. The spatial coordinates change, which you would expect, but the time coordinate also changes, and it changes in a way that depends on both the relative velocity between the frames and the spatial position of the event. This is the key. Time is not independent of space. The time of an event as measured in one frame depends on where the event happens in another frame. This mixing of space and time is what produces the relativity of simultaneity. Let me walk through this more carefully. Suppose two events happen in your frame. Event A happens at position 0 and time 0. Event B happens at some distance away, let us call it delta x, and at the same time, time 0. In your frame, these events are simultaneous. They both happen at time 0. Now imagine an observer moving relative to you at some velocity v. The Lorentz transformation tells us that in the moving observer's frame, event A still happens at a time we can calculate, and event B happens at a different time. The time difference between the two events in the moving frame is not 0. It depends on the distance delta x between the events and the velocity v of the moving observer. Specifically, the time of event B in the moving frame is shifted by an amount that is proportional to v times delta x divided by c squared, where c is the speed of light. If v and delta x are both non-zero, this quantity is not 0. The two events that were simultaneous in your frame are not simultaneous in the moving frame. The larger the spatial separation between the events, the bigger the disagreement. For events that are very close together in space, the disagreement in timing is tiny, essentially unmeasurable in everyday life. This is why you never notice it. The objects in your daily experience are so close together and moving so slowly compared to the speed of light that the relativistic mixing of space and time is negligible. But for events separated by large distances, the effect becomes significant. And for events connected by signals traveling at or near the speed of light, it becomes crucial. It is worth pausing here to appreciate just how revolutionary this idea was when Einstein first proposed it. For thousands of years, philosophers and scientists had assumed that time was absolute. Newton wrote in his Principia that absolute, true, and mathematical time flows equably without relation to anything external. Time was like a river that carried everything along at the same rate. It did not speed up or slow down. It was the same for everyone, everywhere, always. This seemed so obviously true that it was not even questioned. It was not treated as a hypothesis to be tested, but as a self-evident truth about the nature of reality. Einstein demolished this assumption with the single postulate: the speed of light is the same for all observers. From this, the relativity of simultaneity follows as a mathematical necessity. If the speed of light is constant, then time cannot be absolute. If light always travels at c regardless of the observer's motion, then observers in different states of motion must disagree about the timing of distant events. There is no way around it. Absolute time and constant light speed are logically incompatible. You can have one or the other, but not both. The experiments from Michelson-Morley to modern particle physics all confirm that the speed of light is constant. Therefore, absolute time must go. Now, here is where the relativity of simultaneity connects to the light cone structure we explored earlier. The light cone divides events into two categories: time-like separated events, which can be connected by signals at or below light speed, and space-like separated events, which cannot. The simultaneity disagreements we have been discussing apply exclusively to space-like separated events. For time-like separated events, the ordering is absolute. Every observer agrees. But for space-like separated events, the Lorentz transformation can reverse the ordering depending on the observer's velocity. This is the mathematical backbone of what the thought experiments illustrated. The implications run even deeper than cosmic-scale thought experiments. The disagreement about time ordering is not limited to observers in spacecraft traveling at relativistic speeds. It applies to everyone, everywhere, all the time. Two people standing next to each other on a sidewalk, one stationary and one walking at a normal pace, technically disagree on the ordering of distant events. At walking speeds and short distances, the disagreement is immeasurably small. But extend the distance to the Andromeda Galaxy, 2.5 million light-years away, and even walking speed produces a simultaneity shift of days. One person's now in Andromeda is days ahead of the other person's now in Andromeda. Neither is wrong. Both are applying the same physics. The disagreement is built into the structure of space-time itself. You might be wondering how this can possibly be okay. How can the universe function if different observers cannot even agree on the order of events? The answer, as we touched on earlier, is that the disagreement only applies to events that are causally disconnected. No subluminal signal connects them. Neither one caused the other. So the ordering carries no physical significance. It is like asking whether a coin flip in Tokyo or a coin flip in London happened first when the two flips are completely independent. The answer does not matter because neither flip influenced the other. The universe permits disagreement about the ordering of independent events. But for events connected by a causal signal, where one genuinely caused the other, the ordering is absolute. All observers agree, the cause comes first, the effect comes second, always. Let me emphasize this because it is the single most important point in this entire discussion. The universe has a built-in protection mechanism for causality. That mechanism is the speed of light. As long as all causal influences, all signals, all interactions propagate at or below the speed of light, the time ordering of causally connected events is the same for every observer. Different observers might disagree about lots of things. They might disagree about distances. They might disagree about durations. They might disagree about the ordering of unrelated events. But they will never disagree about whether a cause came before its effect. That ordering is sacred. It is protected by the geometry of space-time itself. Now, let me push this a little further, because understanding exactly where this protection comes from and exactly how it works will be essential for understanding what happens when it breaks. Consider two events, A and B, where A causes B. Maybe A is a person throwing a ball and B is the ball hitting a wall. A signal, the ball, travels from A to B. The ball moves slower than the speed of light, so the two events are time-like separated. In every reference frame, every observer agrees that A happened before B. The ball was thrown before it hit the wall. Now boost to a frame moving very fast. The Lorentz transformation changes the coordinates of both events. These spatial and temporal separations both change, but because the events are time-like separated, the time difference between A and B never changes sign. It might get larger or smaller, but it stays positive. A always comes before B. The mathematics guarantees it. Now consider two events that are space-like separated. Event C is a lightning strike in London, and Event D is a lightning strike in Tokyo, and they happen at the same time in your frame. They are too far apart for light to travel between them in the time interval separating them, which is 0. No causal connection exists between them. If you boost to a moving frame, the Lorentz transformation can make either event come first. There exists a frame where C happens before D, a frame where D happens before C, and a frame where they are simultaneous. The time ordering flips depending on the observer's velocity, but this is harmless because no signal connects C and D. Neither one caused the other. This harmlessness is the key to the entire structure. It is what allows the relativity of simultaneity to coexist with a logically consistent universe. The universe permits disagreement about time ordering, but only for events where the ordering does not matter. For events where the ordering does matter, where one event caused the other, the universe enforces unanimous agreement. Everyone sees the cause first. Everyone sees the effect second. There are no exceptions. And the enforcer of this agreement is the speed of light. Think of the speed of light as a gatekeeper. It stands between two regions of space-time. On one side are the time-like separated events, where causal connections exist and the time ordering is absolute. On the other side are the space-like separated events, where no causal connections exist and the time ordering is up for debate. The gatekeeper ensures that nothing crosses from one side to the other. No signal passes from the realm of absolute ordering to the realm of relative ordering. No influence leaks through the boundary. The two regions are sealed off from each other, and the speed of light is the seal. Now here is the critical question. What if you could send a signal faster than light? What if there existed some particle, some pulse, some means of communication that could travel from C to D in less time than light would need? That signal would connect to space-like separated events. C and D would no longer be independent. They would be causally linked by the signal. C would be the cause, the sending event, and D would be the effect, the receiving event. But we just established that for space-like separated events, the time ordering is frame-dependent. Different observers disagree about which happened first, and now these events are connected by a signal. One observer says the signal was sent at C and received at D, with C happening first. That makes sense. The cause came before the effect. But another observer, moving at a different velocity, says D happened before C. In that observer's frame, the signal arrived before it was sent. The effect preceded the cause. This is not a misunderstanding. This is not a matter of correcting for signal delays or accounting for the finite speed of light reaching the observer's eyes. This is a genuine coordinate fact in the framework of special relativity. The Lorentz transformation, applied correctly, produces a negative time interval. The reception event has an earlier time coordinate than the emission event. The signal traveled backward in time, and this is where everything begins to unravel. Because if a signal can travel backward in time in some reference frame, then the universe is no longer logically consistent. Causes and effects become tangled. The past becomes alterable. The future becomes uncertain in a way that goes beyond mere unpredictability. It becomes paradoxical. But we are getting ahead of ourselves. Before we can explore the full consequences of this, we need to look carefully at the mathematics. We need to see exactly how the Lorentz transformation produces a negative time interval for a faster than light signal. We need to understand the hypothetical particle that would carry such a signal, a particle that physicists have given a name, even though it has never been observed. A particle whose very possibility reveals something profound about why the speed of light matters so much. The mathematics is not difficult. It does not require advanced physics or graduate level training. It requires only the willingness to follow the logic wherever it leads, even when it leads somewhere deeply uncomfortable. Because what the equations show is that the speed of light is not just a limit on how fast things can move. It is the barrier that keeps the universe logically coherent. It is the boundary between a cosmos where causes produce effects and a cosmos where effects produce causes. And the equations show, with absolute precision, exactly what happens when that boundary is crossed. What I want you to hold in your mind right now is this. The relativity of simultaneity is real. It is not a philosophical abstraction or a mathematical curiosity. It is a measurable, testable feature of the universe. Different observers in different frames of reference genuinely disagree about the time ordering of certain events. This disagreement is usually harmless because it only applies to events that cannot influence each other. The speed of light ensures that causal connections only exist between events whose time ordering is absolute and agreed upon by everyone. But this entire structure, this entire system of protection, depends on one assumption. It depends on the assumption that no signal, no particle, no influence of any kind can travel faster than the speed of light. If that assumption fails, even once, even for a single particle, then the disagreement about time ordering is no longer harmless. It becomes a disagreement about causality. It becomes a disagreement about which event caused which. And that is not something the universe can tolerate. The question is no longer hypothetical. Physicists have examined it in detail. They have asked what the mathematics of special relativity says about particles that travel faster than light. They have given these hypothetical particles a name. They have worked out their properties, their behavior, and their implications. And what they found is that the consequences of even one such particle existing are far more severe than most people realize. The issue is not just that such a particle would be fast. The issue is that it would make time itself run backward in certain frames of reference. And once time runs backward for even a single signal, the logical structure of cause and effect collapses. We are about to cross the light cone. We are about to follow a hypothetical particle into a region of space-time where the rules we have relied on no longer hold. And what we find there will not be science fiction. It will be mathematics. Pure, precise, and deeply unsettling mathematics that reveals why the speed of light might be the most important number in the universe. Not because of how fast it is, but because of what it protects. In 1962, 3 physicists named Oleksii Myron-Belaniuk, Vijay Deshpande, and E.C. George Sudarshan published a paper that asked a deceptively simple question. What does the mathematics of special relativity actually say about particles that travel faster than light? They were not proposing that such particles exist. They were not claiming to have discovered anything. They were doing something more careful and in some ways more dangerous. They were taking Einstein's equations seriously and following them into territory that most physicists had avoided. Not because the mathematics was wrong, but because the conclusions were disturbing. A few years later, in 1967, the physicist Gerald Feinberg expanded on their work and gave these hypothetical particles a name. He called them tachyons, from the Greek word tachys, meaning swift. The name stuck. And even though more than half a century has passed, and no tachyon has ever been detected, the theoretical analysis of what tachyons would mean for the structure of space-time remains one of the most revealing exercises in all of physics. Not because tachyons are real, but because exploring their consequences exposes the deepest reasons why the speed of light matters. Let me start with the mathematics, because this is where the argument becomes unavoidable. We establish that the Lorentz transformation describes how the coordinates of an event change when you switch from one inertial reference frame to another. Specifically, if an event occurs at position x and time t in one frame, and you boost to a frame moving at velocity v relative to the first, the new time coordinate t prime is given by a specific relationship. The transformed time t prime equals gamma multiplied by the quantity t minus v times x divided by c squared, where gamma is the Lorentz factor, which equals 1 divided by the square root of 1 minus v squared over c squared. This transformation is the backbone of special relativity. It is not optional. It is not approximate. It is the exact mathematical expression of how space and time coordinates change between inertial frames. Now consider a signal. Any signal that travels from event A to event B. Event A is the emission, event B is the reception. In our original frame, the signal is emitted at time 0 and position 0, and received at time delta t and position delta x. The velocity of the signal is delta x divided by delta t. Let us call this velocity u. For an ordinary signal, a light beam, a radio wave, a thrown baseball, u is less than or equal to c. The signal travels at or below the speed of light. Now boost to a frame moving at velocity v in the same direction as the signal. The time interval between emission and reception in the new frame, delta t prime, is given by the Lorentz transformation. Delta t prime equals gamma times the quantity delta t minus v times delta x over c squared. We can rewrite this by factoring out delta t. Delta t prime equals gamma times delta t times the quantity 1 minus v times u over c squared, because delta x equals u times delta t. Remember, u is the velocity of the signal and v is the velocity of the new reference frame. Now look at that expression carefully. Delta t prime equals gamma times delta t times 1 minus v times u over c squared. Gamma is always positive for any observer velocity v less than c. Delta t is positive in our original frame because the signal was emitted before it was received. So the sign of delta t prime, whether the time interval in the new frame is positive or negative, depends entirely on the factor in parentheses, 1 minus v times u over c squared. For an ordinary signal where u is less than or equal to c, this factor is always positive, no matter what v is, as long as v is less than c. You can verify this yourself. If both v and u are less than c, then v times u is less than c squared. So v times u divided by c squared is less than 1, and 1 minus that quantity is positive. Delta t prime remains positive. The signal is received after it is emitted in every frame. The causal order is preserved. This is the mathematical proof of what we discussed earlier. For subluminal signals, the time ordering of cause and effect is absolute. But now, suppose u is greater than c. Suppose the signal travels faster than light. Then something changes. If u is greater than c, then for a sufficiently large observer velocity v, the product v times u can exceed c squared. When that happens, v times u divided by c squared is greater than 1, and 1 minus a number greater than 1 is negative. The factor in parentheses becomes negative. And since gamma and delta t are both positive, delta t prime becomes negative. A negative time interval means the reception happens before the emission. In the boosted frame, the signal arrives before it was sent. Let me be precise about when this happens. The critical condition is v times u greater than c squared, which means v greater than c squared, divided by u. Since u is greater than c, c squared divided by u is less than c. This means the critical observer velocity v is less than the speed of light. It is a perfectly ordinary velocity for a perfectly ordinary observer. You do not need to be moving at some exotic superluminal speed yourself to see the time reversal. You just need to be moving fast enough, and fast enough is always some velocity below c. A normal observer in a normal reference frame moving at a normal subluminal velocity would see the faster than light signal arrive before it was sent. This is the core result. This is what makes tachyons so profoundly problematic. It is not that they would be fast. Lots of things are fast. It is that their superluminal velocity, combined with the Lorentz transformation, which is the exact and experimentally confirmed rule for how coordinates change between frames, produces a negative time interval. The effect precedes the cause, and this happens not in some exotic frame, but in a perfectly mundane one. Let me make this even more concrete. Suppose you have a tachyon emitter on Earth. You fire a tachyon at 5 times the speed of light, toward a detector on a space station 10 light years away. In your frame, the tachyon is emitted now and arrives 2 years from now. The signal travels 10 light years of distance in 2 years of time, which gives a speed of 5 times c. Now consider an observer on a spacecraft moving away from Earth at 60% of the speed of light. This is fast by human standards, but it is a perfectly valid subluminal velocity. For this observer, the Lorentz transformation changes the time interval between emission and reception. When you work through the numbers, the time interval in the spacecraft frame comes out negative. In the spacecraft's frame of reference, the tachyon arrives at the space station before it was emitted from Earth. The space station receives the tachyon before the emitter on Earth fires. The arrival precedes the departure. This is not a paradox of perception. The spacecraft observer is not confused. They are not making a mistake. The Lorentz transformation is exact. The calculation is straightforward. The result is unambiguous. In their frame, using their perfectly valid clocks and rulers, the tachyon objectively arrives at its destination before it leaves its source. Time for this signal runs backward. Now, you might think there is some way around this. Maybe the tachyon's properties are exotic enough that some other rule intervenes to prevent the time reversal. So let us look at what properties a tachyon would actually have. The mathematics of special relativity does not merely tell us that tachyons would be fast. It tells us exactly what they would be like, and those properties are deeply strange. The relationship between energy, momentum, and mass in special relativity is given by a precise expression. The energy squared of a particle equals its momentum squared times c squared plus its rest mass squared times c to the fourth. For an ordinary particle at rest, the momentum is 0, and the energy equals the rest mass times c squared. This is Einstein's famous equation. As you accelerate the particle, its momentum increases, and so does its energy. As the particle approaches the speed of light, the energy grows without bound, approaching infinity. This is why you can never accelerate an ordinary particle to the speed of light. It would require infinite energy. For a photon, the rest mass is 0. The energy equals the momentum times c. Photons travel at exactly the speed of light and have 0 rest mass. This is self-consistent. For a tachyon, something peculiar happens. If you take the same energy-momentum relation and demand that the particle travel faster than light, the mathematics requires that the rest mass squared be negative. Not the rest mass itself, but the square of the rest mass. This means the rest mass is an imaginary number, a multiple of the square root of -1. This is not a physical mass that you could put on a scale. It is a mathematical quantity that appears in the equations and has no direct physical analog. It is one of the reasons physicists have always treated tachyons with deep skepticism. A particle with imaginary mass does not fit neatly into any physical framework we understand. But the strangeness does not end there. For ordinary particles, adding energy makes them go faster. You push a ball and it speeds up. You accelerate a proton in a particle accelerator and it gains velocity. For tachyons, the relationship is reversed. A tachyon with more energy moves slower. A tachyon with less energy moves faster. In the limit of 0 energy, a tachyon would travel at infinite speed. As you add energy to a tachyon, it slows down, approaching the speed of light from above. It gets closer and closer to C, but never reaches it. The speed of light is a barrier for tachyons, just as it is for ordinary particles, but in the opposite direction. Ordinary particles can approach C from below, but never reach it. Tachyons can approach C from above, but never reach it. The speed of light is not just a maximum speed. It is a dividing line. Particles on one side can never cross to the other. This creates a peculiar picture of the particle zoo. There are three classes of particles defined by their relationship to the speed of light. Bradyons, also called tachyons, are particles with positive real mass that always travel slower than light. This includes everything you are made of: protons, neutrons, electrons. Luxons are particles with zero rest mass that always travel at exactly the speed of light. Photons are the best known example, and tachyons would be particles with imaginary rest mass that always travel faster than light. Each class is confined to its side of the light speed barrier. No particle can cross from one class to another. Notice something important here. Even in the tachyon framework, nothing actually accelerates through the speed of light. Bradyons are always below C, luxons are always at C, tachyons, if they existed, would always be above C. The light speed barrier is never crossed by any individual particle. What makes tachyons problematic is not that they break through the barrier. It is that they exist on the other side of it, and the Lorentz transformation tells us exactly what that means for the ordering of events. There is another peculiar feature of tachyons that deserves attention. Because their energy decreases as their speed increases, a tachyon that loses all its energy does not stop. It reaches infinite speed. And a tachyon with infinite speed would be everywhere along its path simultaneously, at least in some frame of reference. This sounds absurd, and in many ways it is. But it is what the equations say. The energy-momentum relation for tachyons is mathematically consistent within the framework of special relativity. The equations do not produce contradictions in the sense of giving two different answers for the same physical quantity. They produce results that are logically coherent but physically bizarre. Now, let me address something that often causes confusion. People sometimes ask whether tachyons could exist, but simply be undetectable. Perhaps they do not interact with ordinary matter, or perhaps they interact so weakly that we have never noticed them. This is a fair question, and the answer requires careful thought. The problem is not detectability, the problem is causality. Even if tachyons were completely invisible, even if they pass through all matter without interacting, their mere existence would create the possibility of causal loops. If any physical process, no matter how obscure, could produce or absorb tachyons, then information could in principle be sent faster than light. And if information can be sent faster than light, the Lorentz transformation guarantees that some observer will see that information arrive before it was sent. The severity of this depends on what you mean by information. If tachyons exist but cannot carry any information, if they are completely random and uncontrollable, then perhaps the causal damage is limited. Some physicists have explored this idea, proposing that tachyons might exist as quantum particles whose behavior is inherently unpredictable, preventing anyone from using them to send a deliberate message. This is called the reinterpretation principle, and it was proposed by Bilaniuk, Sudarshan, and Deshpande. The idea is that in frames where the tachyon appears to travel backward in time, You simply reinterpret the absorption as emission and vice versa. The tachyon's direction is reversed, and the antiparticle interpretation is invoked to maintain consistency. This reinterpretation is clever, but it has significant limitations. It works for individual tachyon events in isolation. But when you try to construct a system that uses tachyons to send signals, the reinterpretation principle runs into serious difficulties. The problem is that the Lorentz transformation is not just a mathematical trick. It reflects the actual physical relationship between reference frames. If a tachyon is emitted at event A and absorbed at event B in one frame, and another frame sees the absorption happen first, then in the other frame, the physical process at B must produce the tachyon rather than absorb it. The causal arrow reverses. The receiving device becomes the emitter, and the emitter becomes the receiver. And if both devices are capable of both emitting and absorbing tachyons, which they must be if any interaction with tachyons is possible at all, then you can construct scenarios where the causal loop closes. A message is sent, received in someone's past, and used to prevent the original sending. We will explore this in full detail shortly, but the point for now is that the reinterpretation principle does not fully resolve the causal problems. Let me also address the world line of a tachyon in space-time because visualizing it makes the problem vivid. In a space-time diagram, where time runs vertically and space runs horizontally, the world line of a stationary object is a vertical line. It stays at the same position and moves forward in time. The world line of an object moving at constant velocity is a line tilted from the vertical. The faster the object, the more the line tilts toward the horizontal. The world line of a photon, traveling at the speed of light, is a line at exactly 45 degrees. This 45-degree line is the light cone boundary. An ordinary particle's world line is always steeper than 45 degrees, always closer to the vertical. It stays inside the light cone. A tachyon's world line would be shallower than 45 degrees, tilted more toward the horizontal. It lies outside the light cone. It connects two events that are space-like separated. Now, when you perform a Lorentz boost, the axes of the space-time diagram rotate. The time axis and the space axis tilt toward each other. For world lines inside the light cone, this rotation never tilts the world line past the horizontal. The world line always has a positive time component. The particle always moves forward in time. But for a world line outside the light cone, a sufficiently large boost can tilt it past the horizontal. The world line, which started with a positive time component pointing toward the future, now has a negative time component. It points toward the past. The tachyon, in this boosted frame, travels backward in time. You can see it directly on the diagram. The world line that was slanting upward and to the right in the original frame is now slanting downward and to the right in the boosted frame. It starts at a later time and ends at an earlier time. It moves into the past. This visual representation makes it unmistakable. The tachyon's world line, lying outside the light cone, is vulnerable to time reversal under Lorentz transformations. The light cone is the boundary. Inside it, world lines are safe. They always point toward the future, no matter what frame you observe from. Outside it, world lines can point in either temporal direction, depending on the frame. The light cone is not just a geometric feature of space-time diagrams. It is the guardian of causality. The history of tachyon research is worth understanding because it shows how seriously physicists have taken this problem. After Bileniuk and Sudarshan's initial paper in 1962 and Feinberg's 1967 analysis, there was a burst of theoretical activity. Dozens of papers explored the properties of tachyons, their possible interactions with ordinary matter, and the causal paradoxes they would create. Experimental physicists also got involved. Several experiments were designed and conducted to search for tachyons directly. One approach looked for particles in cosmic ray showers that appeared to travel faster than light. If a tachyon were produced in a high-energy collision in the upper atmosphere, it might leave a distinctive signature. It would arrive at detectors before the ordinary particles from the same collision, appearing to come from nowhere because its cause, the collision, had not happened yet from the detector's temporal perspective. No such events were ever found. Another approach used particle accelerators. If tachyons could be produced in high-energy particle collisions, they might show up as missing energy or anomalous decay products. Physicists searched for any sign of energy or momentum being carried away by an undetected, faster-than-light particle. Again, nothing was found. Some experiments look for tachyonic Cherenkov radiation. When an ordinary charged particle travels through a medium faster than light, travels through that medium, it emits Cherenkov radiation, a characteristic blue glow. This is the principle behind some neutrino detectors. By analogy, a charged tachyon traveling through vacuum faster than light in vacuum might emit a form of radiation. The theory predicted specific signatures that could be searched for. The searches came up empty. Every experimental test, without exception, has been consistent with the absence of tachyons. No faster-than-light particle has ever been detected by any experiment using any method. The speed of light remains, as far as all evidence indicates, an absolute limit on the propagation of causal signals. Let me tell you more about these searches because the history is revealing. It shows just how seriously physicists took the possibility and how thoroughly they investigated it. The cosmic ray searches were among the earliest and most creative. The logic was straightforward. If tachyons could be produced in high-energy collisions, then cosmic rays, which carry enormous energies far beyond what any human-built accelerator could achieve at the time, would be the most likely source. When a high-energy cosmic ray proton slams into a nitrogen or oxygen nucleus in the upper atmosphere, it creates a shower of hundreds or thousands of secondary particles. These showers have been studied since the 1930s. Physicists know what particles to expect, how many of each type, what energies they carry, and crucially, what timing they should arrive with. If a tachyon were produced in such a collision, it would race ahead of the shower, arriving at ground-level detectors before any of the ordinary particles. It would appear as a precursor signal, a detection event with no apparent cause, followed sometime later by the arrival of the normal particle shower that actually produced it. Several experiments in the 1970s and 1980s were specifically designed to look for these precursor events. Detectors were set up at various altitudes and monitored continuously, with timing systems precise enough to identify particles arriving even a few nanoseconds earlier than expected. The experiments ran for months and in some cases years, accumulating enormous amounts of data. Not a single convincing precursor event was ever found. Every shower arrived in the expected order, with the fastest ordinary particles arriving first and the slower ones trailing behind, exactly as the physics of subluminal particles predicted. The particle accelerator searchers took a different approach. In a controlled laboratory setting, physicists could produce high-energy collisions and examine the products in detail. If tachyons existed and could be produced in particle collisions, they would carry away energy and momentum. This would show up as a discrepancy in the energy balance of the collision. You would add up the energy and momentum of all the detected particles, compare it to the energy and momentum of the initial colliding particles, and find that some was missing. Missing energy is actually a well-established technique in particle physics. It is how the neutrino was first inferred in the 1930s, when Wolfgang Pauli noticed that beta decay seemed to violate energy conservation unless an undetected particle was carrying away the missing energy. If tachyons existed, a similar signature could appear, but with a distinctive pattern. Because tachyons have imaginary mass and their energy-momentum relation is different from ordinary particles, the missing energy and momentum would fall in a specific region of parameter space that is different from what neutrinos or any other known particle would produce. Physicists searched for this signature at multiple accelerator facilities throughout the 1970s and 1980s. They examined millions of collision events, looking for any case where the missing energy pattern matched what a tachyon would produce. Every search came up empty. The energy books balanced perfectly once all known particles were accounted for. No room was left for tachyons. The Cherenkov radiation searches were perhaps the most elegant. When a charged particle travels through a transparent medium faster than light, travels through that medium, it emits a characteristic cone of blue light called Cherenkov radiation. This is the electromagnetic equivalent of a sonic boom. A boat moving faster than the speed of water waves creates a wake. A jet moving faster than the speed of sound creates a shock wave. A charged particle moving faster than the local speed of light creates Cherenkov radiation. This phenomenon is well understood and is actually used routinely in particle physics detectors. Now, in a normal medium like water or glass, light travels slower than it does in a vacuum. Ordinary particles can exceed this reduced speed and produce Cherenkov radiation. But in a vacuum, nothing can exceed the speed of light. So Cherenkov radiation does not occur, unless tachyons exist. A charged tachyon, traveling through vacuum faster than the speed of light in vacuum, would theoretically emit a form of vacuum Cherenkov radiation. The characteristics of this radiation, its spectrum, its angular distribution, its intensity, were calculated by several theorists. Experimentalists then look for it. They set up sensitive photon detectors in vacuum chambers, shielded from all known sources of light, and they waited. They looked for the distinctive spectral signature that vacuum Cherenkov radiation would produce. They looked in the vicinity of particle collisions where tachyons might have been created. They looked in cosmic ray data for photon patterns consistent with tachyonic emission. In every case, the result was the same: nothing. No vacuum Cherenkov radiation was ever detected. No photon pattern matched the tachyonic prediction. The vacuum remained dark and silent, consistent with a universe in which nothing travels faster than light. There was even a search based on the possibility that tachyons might have a tiny electric charge or might interact with the electromagnetic field in some other way. If tachyons were constantly being produced and absorbed in the quantum vacuum, their fleeting existence might leave subtle traces in precision measurements of electromagnetic phenomena. Physicists looked for anomalies in the Lamb shift, in the magnetic moment of the electron, in the Casimir effect, in every high-precision electromagnetic measurement they could think of. The measurements agreed with the predictions of standard quantum electrodynamics to extraordinary precision, sometimes to more than 10 decimal places. There was no room for tachyonic contributions. The quantum vacuum behaved exactly as expected for a universe with no faster-than-light particles. But the absence of evidence, while significant, is not the deepest reason physicists doubt tachyons exist. The deepest reason is the causal argument. The Lorentz transformation is not a hypothesis. It is a consequence of the two postulates of special relativity, both of which have been confirmed to extraordinary precision. If tachyons exist and can interact with ordinary matter in any way, the Lorentz transformation guarantees that some observer will see signals traveling backward in time. And once signals travel backward in time, the logical structure of cause and effect collapses. This is not a technical difficulty that might be solved with clever engineering or new physics. It is a mathematical certainty within the framework of special relativity. Some physicists have speculated that perhaps special relativity itself breaks down at superluminal speeds, that some new physics takes over and prevents the causal paradoxes. This is possible in principle, but there is no evidence for it. Special relativity has been tested to extraordinary precision across a wide range of conditions, and it has never failed. Any theory that replaces it would need to reproduce all of its successful predictions while simultaneously allowing faster-than-light particles without causal paradoxes. No one has constructed such a theory. Others have suggested that quantum mechanics might help. In quantum field theory, the framework that combines quantum mechanics with special relativity, there are situations where quantities related to the speed of light appear to be exceeded. Virtual particles, which are mathematical terms in perturbation theory, rather than real observable particles, can have space-like form momenta. Quantum tunneling can appear to allow particles to traverse barriers faster than light. But in every case that has been carefully analysed, no usable information travels faster than light. The signal velocity, the speed at which you can actually send a message, remains at or below c. The quantum world is strange, but it does not violate relativistic causality. The tachyon, then, stands as one of the most instructive theoretical constructs in physics. It has never been observed. It may be fundamentally impossible, but the analysis of what it would mean if it existed reveals something deep about the architecture of the universe. The speed of light is not an arbitrary speed limit imposed by some cosmic traffic authority. It is the structural feature of space-time that makes cause and effect possible. The mathematics shows this with a clarity that no thought experiment or intuitive argument can match. The Lorentz transformation, applied to a superluminal world line, produces backward time travel, not metaphorically, not approximately, exactly and unavoidably. And the consequences of backward time travel for signals are not merely strange, they are catastrophic. because once you have a signal that arrives before it is sent, you can use it to construct something far worse than a particle that moves in the wrong temporal direction. You can construct a device that sends messages into its own past. You can create a closed causal loop where an effect erases its own cause. You can build what physicists have called a tachyonic antitelephone. And when you do, the entire framework of cause and effect does not merely bend, it shatters. In 1970, 3 physicists named Gregory Benford, David Book, and William Newcomb published a paper that described something remarkable. They showed that if tachyons exist and can be used to transmit information, you could build a device that sends messages into its own past. They called it the tachyonic antitelephone. The name sounds almost playful, like something out of a comic book, but the argument behind it is airtight. It follows directly from the Lorentz transformation, the same transformation that has been confirmed by every experiment in the history of modern physics. And it demonstrates, with mathematical precision, exactly why faster-than-light signaling would destroy the logical structure of causality. Let me walk you through the construction step by step, because the logic is what matters here, not the engineering. The engineering is hypothetical. The logic is exact. Imagine 2 observers, Alice and Bob. Alice is on Earth. Bob is on a spacecraft moving away from Earth at some significant fraction of the speed of light. Both Alice and Bob have tachyon transmitters and receivers. These devices can send and receive tachyons, hypothetical particles that travel faster than light. Alice sends a tachyon message to Bob. In Alice's reference frame, the tachyon travels faster than light and arrives at Bob's location sometime after it was sent. From Alice's perspective, everything looks normal. She sent a message and it arrived. The cause preceded the effect. No problem so far. But now consider the same event from Bob's reference frame. Bob is moving relative to Alice. Because of the Lorentz transformation, the time interval between Alice's emission and Bob's reception is different in Bob's frame than it is in Alice's frame. And as we showed in detail, for a sufficiently fast tachyon and a sufficiently fast relative velocity between Alice and Bob, the time interval in Bob's frame becomes negative. In Bob's frame, he receives the tachyon before Alice sent it. The reception happens first, the emission happens second. The message arrives before it departs. Now, here is where the catastrophe begins. Bob receives the message. According to his own clocks, the message arrived at some particular time. He then uses his own tachyon transmitter to send a reply back to Alice. He sends this reply at some time after he received Alice's message, according to his clocks. This is perfectly normal from Bob's perspective. He received something, then he responded. Cause followed by effect. But Bob's reply is also a tachyon. It also travels faster than light. And now we need to analyze the second tachyon signal from Alice's frame. Alice is moving relative to Bob, just as Bob is moving relative to Alice. The Lorentz transformation applies in the other direction as well. And once again, for the right combination of tachyon speed and relative velocity, the time interval for Bob's reply signal becomes negative in Alice's frame. Alice receives Bob's reply before Bob sent it. Now put both signals together. Alice sends a tachyon to Bob. Bob receives it and sends a reply. Alice receives the reply. But when does Alice receive the reply? She receives it before she sent the original message. The reply arrives in Alice's past. She gets Bob's response before she asks the question. The entire round trip, outgoing message and return reply forms a closed causal loop that curves backward through time and deposits information in Alice's own past. Let me put concrete numbers to this so you can see that this is not some edge case requiring absurd velocities or impossible configurations. Suppose Bob is moving away from Alice at 60% of the speed of light. Alice sends a tachyon at 3 times the speed of light. In Alice's frame, the tachyon travels outward, reaches Bob, and arrives sometime after it was sent. But in Bob's frame, the time interval comes out negative. The tachyon arrives before it was sent. Bob immediately fires a tachyon reply back toward Alice, also at 3 times the speed of light in his frame. In Bob's frame, his reply is sent after he received Alice's message. But in Alice's frame, because Bob is moving and because his tachyon is also superluminal, the Lorentz transformation again produces a negative time interval. Alice receives the reply before she sent the original message. The round-trip backward time shift is not enormous. It is not centuries or millennia, but it is real and it is non-zero. Even a single nanosecond of backward time travel for a signal is enough to create the paradox. The size of the time shift does not matter. What matters is that it is negative. The effect precedes the cause, and the velocities involved are not extreme. Bob is traveling at 60% of the speed of light. Fast certainly, but well within the range of velocities that are physically meaningful. The tachyons travel at 3 times the speed of light, which is modest by tachyon standards, since tachyons with less energy would travel even faster. None of the numbers are pushed to absurd limits. The paradox arises naturally, easily, almost casually, from perfectly reasonable parameters. This is what makes it so dangerous. It is not a fragile result that depends on fine-tuned conditions. It is a robust result that appears over a wide range of tachyon speeds and observer velocities. Let me be absolutely clear about what this means. This is not an observer in a distant frame seeing events in a confusing order. This is Alice, sitting at her desk on Earth, receiving a reply to a message she has not yet sent. The reply is in her hands. She can read it. It contains information about a question she was going to ask, but has not asked it yet. The effect, receiving the reply, has preceded the cause, sending the question, in Alice's own reference frame, according to Alice's own clocks, in her own experience of time. And now Alice has a choice. She can read the reply and decide not to send the original message. Maybe the reply says something she does not like. Maybe it warns her of a bad outcome. Whatever the reason, she chooses not to send the message that prompted the reply. But if she never sends the message, then Bob never receives it. If Bob never receives it, he never sends the reply. If Bob never sends the reply, Alice never receives it. But she did receive it. That is what prompted her to not send the message. The effect has erased its own cause. The causal chain eats itself. This is a genuine logical paradox. It is not a matter of interpretation or philosophical hand-waving. It is a contradiction. The reply both exists and does not exist. The message was both sent and not sent. The universe would need to be in 2 mutually exclusive states simultaneously, not in the quantum mechanical sense where superposition is a well-defined mathematical framework, but in the classical sense where a macroscopic event both happened and did not happen. This is not quantum uncertainty. This is logical impossibility. The tachyonic antitelephone is often compared to the grandfather paradox of time travel fiction. In the grandfather paradox, a person travels back in time and prevents their own grandparents from meeting, thereby preventing their own birth, which means they could never have traveled back in time to prevent the meeting. The tachyonic antitelephone is the same structure, but it does not require a time machine. It does not require exotic wormholes or bent space-time or any speculative physics beyond one single assumption: that a signal can travel faster than the speed of light. That is the only ingredient. The rest, the causal loop, the paradox, the logical contradiction, follows automatically from the Lorentz transformation, which is the most well-tested piece of mathematics in modern physics. This is why the tachyonic antitelephone argument is so devastating. It does not depend on exotic physics. It depends on the most ordinary, well-established physics we have. Special relativity is not speculative. It is the foundation of particle physics, electromagnetism, nuclear physics, and cosmology. The Lorentz transformation is used every single day in laboratories around the world. It is built into the design of particle accelerators, into the calibration of GPS satellites, into the analysis of astronomical observations. And this same transformation, applied to a faster-than-light signal, produces backward-in-time communication. There is no loophole. There is no escape clause. The mathematics is exact. Some people have proposed solutions to the paradox. One popular idea is the Novikov self-consistency principle, which states that any event in a causal loop must be self-consistent. The universe would somehow arrange itself so that paradoxes never actually occur. If Alice receives a reply from the future, then whatever she does with that information, she will still end up sending the original message. The chain of events forms a consistent loop with no contradictions. This is an interesting idea, but it raises deep problems of its own. It implies that the universe constrains free will, or at least constrains the outcomes of physical processes to prevent paradoxes. Alice might read the reply and decide not to send the message, but somehow, something would always prevent her from following through on that decision. Maybe the transmitter malfunctions, maybe she changes her mind, maybe some chain of events forces the message to be sent regardless. The universe would have to conspire actively and precisely to prevent any inconsistency. This is not impossible in principle, but it implies a level of cosmic fine-tuning that most physicists find deeply uncomfortable. It also raises the question of what physical mechanism enforces the consistency. Known physics has no such mechanism. There is no force of self-consistency, no field that detects impending paradoxes and intervenes to prevent them. The Novikov principle describes what must happen, but it cannot explain how or why. Another proposed solution is the many worlds interpretation, where each time a paradox would occur, the universe splits into branches. In one branch, Alice sends the message. In another, she does not. The paradox is avoided because the cause and effect exist in different branches. But this does not really solve the problem for the tachyonic antitelephone. The branching would need to happen at exactly the right moments and in exactly the right way to prevent information from the future from creating contradictions. And it would mean that faster-than-light signaling does not just violate causality, it fractures reality into an ever-multiplying cascade of parallel timelines. This is not a resolution. It is a different kind of catastrophe. There is a third approach that deserves attention. Some physicists have suggested that perhaps the emission and absorption of tachyons cannot be controlled. If tachyon production is inherently random, like radioactive decay, and if you cannot choose when to emit a tachyon or encode information onto it, then perhaps tachyons could exist without enabling the antitelephone. The idea is that the paradoxes only arise when you can use tachyons to send deliberate messages. If tachyons are uncontrollable, they cannot carry information, and the causal loop cannot close. This is a more subtle argument, and it has some merit. If tachyons were purely random quantum events with no controllable properties, then it might be technically true that no information travels backward in time, even though the particles themselves do in some frames. The problem is that this requirement is extremely restrictive. It would mean that tachyons cannot interact with any controllable system in any predictable way. They cannot be emitted by any device that can be turned on and off. They cannot be absorbed by any detector that produces a measurable result correlated with the emission. They would have to be, in a very precise sense, completely decoupled from any physical system that could exploit their superluminal nature. And if they are that decoupled, it becomes unclear in what sense they exist at all. A particle that cannot interact with anything, that cannot be produced or detected or influenced by any physical system, is indistinguishable from a particle that does not exist. This approach saves tachyons from paradox only by stripping them of any physical relevance. The most widely accepted conclusion among physicists is simpler. Tachyons that can carry information do not exist. The reason is not that some unknown mechanism prevents the paradoxes. The reason is that the universe does not allow faster than light signaling in the first place. That speed of light is not just a speed, it is a constraint on causality itself. The universe enforces this constraint, and the tachyonic antitelephone argument shows us exactly why it must. Now, I need to clarify something important because the word tachyon does appear in modern physics, and its meaning is subtly different from the faster-than-light particles we have been discussing. In quantum field theory, which is the framework that combines quantum mechanics with special relativity, a tachyonic field is a field whose mass parameter squared is negative. This is the same mathematical signature as the tachyon particles we discussed. But in quantum field theory, a negative mass squared does not produce particles that travel faster than light. Instead, it signals an instability in the field. Think of it like this. Imagine a ball sitting on top of a hill. Mathematically, the top of the hill is an equilibrium point. The ball could sit there in principle, but it is an unstable equilibrium. The slightest nudge and the ball rolls down. A tachyonic field is like that ball on the hilltop. The field is sitting at an unstable configuration. The negative mass squared means the field is at a maximum of its potential energy, not a minimum. The field will roll down to a more stable configuration, a process called tachyon condensation. After it reaches the stable minimum, the field no longer has a negative mass squared. The tachyonic behavior disappears. The instability resolves itself. The most famous example of this process is the Higgs mechanism. The Higgs field in the standard model of particle physics has a tachyonic mass parameter in its original symmetric state. This means the state where the Higgs field is zero everywhere is unstable. The field spontaneously rolls to a non-zero value. breaking the electroweak symmetry and giving mass to particles like the W and Z bosons. This is not a faster-than-light phenomenon. No tachyon particles are produced. No signals travel faster than light. The word tachyonic in this context refers to the instability of the field, not to superluminal particles. The Higgs boson that was discovered at the Large Hadron Collider in 2012 is a perfectly ordinary particle that travels slower than light. It is the quantum excitation of the Higgs field around its stable minimum, not a tachyon in the superluminal sense. The tachyonic instability occurred in the early universe when the field was at its unstable maximum. It resolved itself almost instantly as the field condensed to its current value. No faster-than-light particles were involved at any point. This distinction is important because it shows that even when tachyonic mathematics appears in well-established physics, the result is never faster than light particles. The mathematics channels itself into instabilities and phase transitions rather than into causality violations. It is as though the structure of quantum field theory knows about the causal constraints and automatically avoids producing anything that would violate them. The equations seem to protect causality on their own. This pattern repeats throughout physics. There are many situations where something appears to travel faster than light, and in every case, when you analyze it carefully, no information actually exceeds the speed of light. The phase velocity of certain waves can exceed c, but phase velocity does not carry information. The group velocity in some media can appear superluminal, but the signal velocity, the speed at which a sharp pulse front travels, remains at or below c. Quantum entanglement produces correlations between distant particles that appear to be instantaneous, but these correlations cannot be used to send a message faster than light. The correlations are only visible after the two observers compare their results, and that comparison requires a classical signal traveling at or below c. Even the expansion of the universe, which causes distant galaxies to recede from us faster than the speed of light, does not violate causality. The galaxies are not moving through space faster than light. Space itself is expanding, carrying the galaxies with it. No information is being transmitted from one galaxy to another at superluminal speed. The expansion is a property of the metric of space-time, not a motion of objects through space. A galaxy receding from us at twice the speed of light due to cosmic expansion is not sending any signal to us at superluminal speed. It is simply being carried away by the stretching of space, and the light it emits is being stretched along with it, redshifted into longer and longer wavelengths, until eventually it becomes undetectable. The galaxy is not violating the speed limit. It is not even moving in the usual sense. The space between us is simply growing. Every apparent superluminal phenomenon, without exception, turns out to respect the causal speed limit when analyzed carefully. The universe appears to have an ironclad rule. No information, no signal, no causal influence travels faster than light. And the tachyonic antitelephone argument shows us why that rule must hold. It is not an arbitrary restriction. It is the price of logical consistency. Without it, cause and effect collapse. So where does this leave us? What is the verdict of physics on the tachyon? The tachyon is a valid mathematical solution within the equations of special relativity. The equations do not forbid particles with imaginary mass that travel faster than light. They describe such particles with the same mathematical precision that they describe ordinary particles. The energy-momentum relations are consistent. The Lorentz transformation applies to them without contradiction in the purely mathematical sense. Tachyons are not a flaw in the theory. They are a feature, a possibility that the mathematics permits. But the physical consequences of that possibility are unacceptable. Tachyons that can carry information lead directly and unavoidably to causal paradoxes. The tachyonic antitelephone can be constructed from nothing more than two tachyon emitters and the Lorentz transformation. It sends messages into the past. It creates logical contradictions, and there is no known mechanism within the framework of special relativity that prevents these contradictions from occurring. Experimentally, no tachyon has ever been detected. No particle has ever been observed traveling faster than light. No experiment has ever found evidence of any signal propagating at superluminal speed. The speed of light remains the universal speed limit for all causal processes. Every test, from particle physics to astronomy to precision measurements of space-time itself, is consistent with this limit. In 2011, an experiment called Opera initially reported that neutrinos had traveled from CERN in Switzerland to the Gran Sasso laboratory in Italy faster than the speed of light, arriving 60 nanoseconds earlier than light would have. The announcement sent shockwaves through the physics community. If confirmed, it would have been the first direct evidence of superluminal particle propagation. But within months, the Opera collaboration identified the cause: a loose fiber optic cable connecting a GPS receiver to an electronic timer. The faulty connection introduced a delay in the timing synchronization that made the neutrinos appear to arrive early. When the cable was fixed and the experiment was repeated, the neutrinos arrived at exactly the time expected for particles traveling at or just below the speed of light. The result was a measurement error, not new physics. And its resolution reinforced what every other experiment had shown. The speed of light holds. In quantum field theory, tachyonic fields do appear, but they do not produce faster than light particles. They produce instabilities that resolve into ordinary physics through processes like tachyon condensation and symmetry breaking. The Higgs mechanism, one of the cornerstones of the Standard Model, involves a tachyonic instability, but the result is not superluminal particles. It is the generation of mass for ordinary particles through a perfectly causal process. The consensus among physicists today is that tachyons as faster than light particles do not exist. They are theoretical constructs that arise in the mathematics of special relativity, but are excluded by the requirement that the universe be causally consistent. The speed of light is not merely a speed, it is the boundary that separates a logically coherent universe from a logically incoherent one. Crossing that boundary even once, even for a single particle, would unravel the entire structure of cause and effect. And this is perhaps the deepest lesson of the tachyon. Not a lesson about speed or about exotic particles, but a lesson about the nature of physical law. The speed of light is special not because of how fast it is. 300,000 kilometers per second is just a number. In different units, it is a different number. What makes it special is its role in the structure of space-time. It is the speed at which the geometry of Minkowski space-time divides causal from acausal, reachable from unreachable, past from future. It is the speed embedded in the Lorentz transformation, the speed that ensures the consistency of physical law across all reference frames. When Einstein published Special Relativity in 1905, he was motivated by a puzzle about light and electromagnetism. He wanted to understand why Maxwell's equations, which describe electromagnetic waves, give the same speed of light regardless of the observer's motion. The answer required rethinking the nature of space and time, but the consequences went far beyond electromagnetism. They revealed that the speed of light is woven into the deepest structure of reality. It connects space and time into space-time. It defines the light cone. It determines which events can cause which other events. It protects the logical order of cause and effect. And the tachyon, by threatening to violate that order, shows us just how essential this speed really is. A particle that has never been found. A particle that probably cannot exist. And yet, by exploring what it would mean if it did exist, we learn something extraordinary about the universe we actually live in. We learn that the speed of light is not a barrier in the way a wall is a barrier. Something that is simply in the way. It is a barrier in the way that logic is a barrier. You cannot violate it because violating it would make the universe self-contradictory. The speed of light is the speed of causality. And causality is not optional. Think about what that means for a moment. We live in a universe where the structure of space-time itself prevents logical contradictions. The geometry of the cosmos is arranged so that causes always precede effects, not because some external law is imposed from outside, but because the fabric of space-time is built that way. The light cone is not a rule about light, it is a rule about reality. It defines what can influence what. And the tachyon, by its hypothetical existence, illuminates that boundary more clearly than any ordinary particle ever could. We learn more about why the light cone matters from exploring what would happen if it were violated than we learn from any observation that respects it. The tachyon is a theoretical flashlight pointed at the foundations of physics, and what it reveals is that those foundations are deeper and more rigid than they might appear. The next time you see a beam of light, a flashlight cutting through the dark, a street light illuminating the road, sunlight streaming through a window, remember that the speed at which that light travels is more than just a fast speed. It is the universe's deepest structural constant. It defines the relationship between space and time. It determines the boundary between the possible and the impossible. It is the reason why causes come before effects, why the past leads to the future, why the universe makes sense at all. And somewhere in the mathematics of special relativity, there is a hypothetical particle that would violate all of this. A particle that would reverse the arrow of time, shatter causality, and make the universe logically incoherent. That particle has never been found, and the equations themselves tell us why it probably never will be. Because the universe, it seems, does not allow paradoxes. It does not allow effects before causes. It does not allow messages from the future that erase themselves. The mathematics is beautiful, precise, and unforgiving. And the verdict is clear. The speed of light is not merely fast, it is necessary. And the particle that would reverse time remains exactly where it belongs. In the equations, as a warning, as a boundary marker, illuminating the edge of what is possible by showing us what would happen if we crossed it. That edge is real. That boundary is absolute. And it tells us something profound about the universe we are privileged to inhabit. The cosmos is not a chaos of events happening in random order. It is a structured, ordered, logically coherent system where causes produce effects, where the past determines the future, where the arrow of time points reliably forward. And all of this, every bit of it, is protected by a single number. The speed at which light crosses the void. 300,000 kilometers per second. Not fast. Necessary.